Hello everyone. In this video, we'll be learning about how to solve this magnetic field question on the board. Now, the question reads, a capacitor is placed between the poles of a large magnet as shown in the figure above. So we have the two poles of the large magnets we have the south pole and the north pole. We know that a magnet has two poles, and that's the north and the south pole. Then also we have that in the spacing between the plates of the capacitor, there is a uniform electric field E and also a uniform magnetic field B. Okay, a uniform magnetic field B. Now, the two fields are parallel and in the direction of Z. So that means that the lines of induction of the electric field and the magnetic field, okay, are parallel to each other. And we also have that the electric field and the magnetic field have their direction in the Z direction. Okay, that means they are parallel and in the direction of Z. So which means we are going to consider the unit vector in the Z direction. Okay, so we have a small sphere carrying charge Q equals to 3 microcoulomb has instantaneous velocity U, which is this. If D equals to 40 millimeters. Now, D is the what? Is the distance of separation between the plates of the capacitor. And we're also giving the electric field potential. Okay, the electric field potential is 2000 volts. And we're also giving the magnetic flux density to be 1.5 Tesla. So, what is the instantaneous force on the sphere? What is the instantaneous force on the sphere? Now, let's have our solution. What is the instantaneous force on the sphere? Now, we know that the magnitude of the charge we are given is what? 3 microcoulomb. And that will be 3 times 10 raised to the what? Power of minus 6 coulombs. Okay. Then we're also giving the magnitude of the instantaneous velocity, which is 4 times 10 raised to the power of 4. Okay. Open parentheses, 0.766 J, which is a unit vector in the y direction. Okay. And then we also have 0.643 K, which is the unit vector in the Z direction. Okay. Now, and we have the units to be in what? Meters per second. Now, we're also giving the distance. Okay. The distance between the plates of the capacitor to be 40 millimeters, which will be 0.04 meters. Okay, 0.04 meters. Then also we are giving the electric field potential to be 2000 volts. The electric field potential is 2000 volts. And we're also giving the magnitude of the magnetic flux density to be 1.5 Tesla. All right. Now, because we are giving that that's the electric field and the magnetic field, they are uniform and they are both moving in the direction of Z. So that means that we're going to consider the unit vector in the direction of Z. All right, for both electric field, the electric field vector and the what? Magnetic field vector. But first, what is our electric field vector? Now, we know that electric field can be measured in terms of potential gradient, and it is the ratio of the field potential to the what? Distance between the plates of the capacitor. So we have 2000, that is, we have the field potential, okay, over what? Distance between the plates of the capacitor. Now, because the direction is in the Z direction, so we have the unit vector to be what? K. All right. So K is a unit vector in the direction of Z. Okay. Now, so this will be 2000, okay, divided by 0.04, which is the distance between the plates of the capacitor. Okay. So when we divide 2000 by 0.04, okay, 2000, okay, divided by 0.04, that will be 50,000. That will be 50,000, which is 5 times 10 raised to the power of 4. Okay. 5 times 10 raised to the power of 4. Now, the unit vector is K. and that will be, the unit will be in what? Volt per meters. All right. So that's the unit vector in the what? In the direction of Z. Then also the magnetic field vector, because we are giving the magnitude of B to be what? 1.5 Tesla. So the magnetic field vector in the direction of Z will be 1.5 K. And the unit of this is what? Is the Tesla. All right. Now, so now we can see that the electric charge, that is the charge, exists in the region of both electric field and magnetic field. So the electric charge will experience a force, okay, whose magnitude will be equal to the vector sum of the electric force and the what? Magnetic force. And that is the Lorentz equation. So we are going to use, okay, using Lorentz equation. Okay, using Lorentz equation, we have F equals to the electric force to be plus the what? Magnetic force. And we know that this will be, the electric force will be Q times the electric field vector, and the magnetic force will be Q times the instantaneous velocity and the what? Magnetic field vector. Okay, magnetic field vector. All right, so we can write this as Q parenthesis E, which is the electric field vector, and then U, then multiplied by the magnetic field vector. So now let's plug in the values we're given. So we have the magnitude of the electric charge is 3 times 10 raised to the power of minus 6. Now the electric field vector is 5 multiplied by 10 raised to the power of 4. Remember, the unit vector is what? In the direction of Z. All right, then plus the instantaneous velocity. So we have the instantaneous velocity to be 4 times 10 raised to the power of 4. Okay, then open parenthesis 0.766J plus 0.643K. Then we are now going to multiply by what? The magnetic field vector, which is 1.5 K. Then we close the parenthesis. All right. Now let's get the value for what is 4 times 10 raised to the power of 4 multiplied by 1.5 K. Okay. 4 times 10 raised to the power of 4 multiplied by 1.5 K. That will be 60,000, which is 6 times 10 raised to the power of 4K. So we then have F equals to 3 times 10 raised to the power of negative 6. Okay, then 5 times 10 raised to the power of 4. Then the unit vector is K, all right, in the direction of Z. So we have 60,000, which will be 6 times 10 raised to the power of 4K. Then into bracket 0.766J plus 0.643K. Then close the parenthesis. All right. So now we can distribute 3 times 10 raised to the power of minus 6 into what we have here. Okay. Now, when we multiply 5 times 10 raised to the power of 4, which is 50,000, when it is multiplied by 3 times 10 raised to the power of minus 6, okay, that will be 0.15. So we have F equals to 0.15 K, okay, because we have the unit vector in the direction of what? Z. Then let's multiply 3 times 10 raised to the power of minus 6 by 6 times 10 raised to the power of 4K. All right, so we have 60,000 multiplied by 3 times 10 raised to the power of minus 6, and that will be 0.18. So we then have plus 0.18K into 0.766J plus 0.643K. All right. Now, in this case, we still need to expand this. That is, we need to distribute 0.18K in this case. So when we distribute 0.18K into 0.766J plus 0.643K. Now, this is important. Now, when we talk about, there's what we call cross product of vector. Now, when we talk about cross product of vector, now here are some of the key terms. Okay, here are some of the key terms. We know that the cross product of, that is I times I, will be what? 0. Okay. J times J will be what? 0. K times K will be what? 0. But when we have I times J, that will be K. Okay. J times K, that will be what? I. Then also, if we have K times J, that will be what? Negative I. Okay. So, which means when we multiply 0.18K by 0.766J, okay, we're going to have negative, that's 0.18 multiplied by 0.766. Okay. That will be 0.138, and that will be negative 0.138I. So that means F will be equals to 0.15K minus, because K times J, remember cross product, K times J is what? Negative I. And that will be what? Minus 0.138I. Okay, now when we multiply 0.18K by 0.643K, now because we have K times K to be what? 0. K times K, that's the cross product, okay, of K, and that's one multiply times K, that's the cross product, okay, of K, and that's one multiply K times K using cross product, that'll be 0. So which means multiplying this by 0.643K, that makes that what? That'll make that'll be 0. So the instantaneous force will then be written as negative 0.38I, okay, plus 0.15K. And this is the what? Instantaneous force on the sphere. This is the instantaneous force on the sphere. And don't forget that the unit of force is the what? Newton. Thank you.